am R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this video, we are going to see the topic of capacitance of isolated sphere and spherical cells. And for finding the capacitance of a spherical capacitor, consider a spherical capacitor formed by two concentric spherical conducting shells of radius A and B. And the radius of outer sphere is considered as B and the radius of inner sphere is considered as A. In between the two spherical shells, the permittivity is the dielectric material having the permittivity epsilon is filled, and the inner sphere is having with the positive charge plus Q, and let the outer sphere is having the negative charge minus Q. So considering the Gaussian surface as a sphere of radius r, we can write the electric field expression in radial direction is equal to Q by 4 pi epsilon r squared AR volts per meter. And the potential difference, that is the work done by moving a unit positive charge against the direction of electric field, that is from r is equal to B to r is equal to A, is given by V is equal to minus negative to positive the limits of integral E dot dl, which is equal to by substituting the values of E, the integral of r is equal to B to A Q by 4 pi epsilon r square AR dot dl. So this is the potential difference equation. So next is this differential length dl can be written as dr into AR vector because their electric field is in radial direction. So by substituting dl value in the potential difference formula, we can be written as minus integral of r is equal to B to r is equal to A Q by 4 pi epsilon r square AR dot dr AR. So here AR dot AR vector is equal to 1. So that can be eliminated. So the potential difference formula becomes integral of minus integral of r is equal to B to A Q by 4 pi epsilon r square dr. So here Q by 4 pi epsilon is a constant, it is taken outside of the integration. So the integral value is integral of r is equal to B to A 1 by r squared into dr. So we know that integration of 1 by r squared into dr is minus 1 by r, and the limit is substituted. So the upper limit A, the lower limit is B. So we get the potential difference equation V is equal to Q by 4 pi epsilon 1 by A minus 1 by B volts. So now we can easily get the capacitance formula by substituting the value of charge Q by the potential difference V. So Q is substituted and V is written as Q by 4 pi epsilon 1 by A minus 1 by B from our determination. So this Q get cancelled, the 4 pi epsilon r will go to the numerator. So the capacitance, the final formula of a spherical capacitor, C is equal to 4 pi epsilon divided by 1 by A minus 1 by B, and the unit is farads. So this is the capacitance value of a spherical capacitor. And now next we are going to see the capacitance of a single isolated sphere. So consider we have only single sphere of radius A and there is no outer plate, and the outer plate is considered as infinitely large, that is the radius of outer sphere B is kept infinity. So in this case, substituting the value of B as infinity in the formula, the capacitance formula, C is equal to 4 pi epsilon divided by 1 by A minus 1 by infinity. We know that 1 by infinity is 0. So this capacitance formula becomes 4 pi epsilon naught divided by 1 by A. This A is taken to the numerator. So the final value of capacitance C for a single isolated sphere, that is no outer sphere is at infinite distance. So C is given as 4 pi epsilon A farads. So in this case of spherical capacitor, the conductor is spherical conductor at a large distance from other conductors, and practically this is very important because this is useful for obtaining stray capacitance of an isolated body. And next, third case, we are going to see the capacitance of single isolated sphere, but it is coated with a dielectric material. So in this case, consider a single isolated sphere, and as usual, as in the previous case, the outer sphere is considered as it is at a very large distance, it is infinitely large. So single isolated sphere is coated with a dielectric having the permittivity epsilon 1. So this dielectric material is up to the radius R1. So the radius of the inner sphere is A, which is shown in figure, and it is placed in free space. So outside sphere is epsilon is equal to epsilon naught. So only we have the inner sphere is coated with dielectric material, and there is no outer sphere, it is at large distance. So the permittivity, the dielectric medium is air medium, so permittivity is epsilon naught. So we have two limits here. One is the radius value from A to R1, the value of permittivity of a dielectric material is epsilon 1. And next is after R is equal to R1, that is beyond this R1, we have the air medium, because the outer sphere is at very large distance. So here for air medium, the dielectricity is taken as epsilon naught. So here there are two cases of radius, one is up to R1 and beyond R1. Up to R1, the permittivity of the dielectric is epsilon 1, and beyond R1, the permittivity of dielectric material is epsilon naught. So now the potential difference are work done by bringing the unitive positive charge from outer sphere to inner sphere, that is R equal to A against the electric field from R infinity to R equal to A. So this can be splitted by two terms. One is V is equal to minus E dot dl from R equal to infinity to A, and another one is V is equal to minus of integral R is equal to R1 to A, E dot dl. So for the first case, the E1 can be obtained as Q by 4 pi epsilon 1 R squared AR, and for the second case it is Q by 4 pi epsilon naught R squared AR. So here this dl is the radial vector, and so it is dr AR vector. So finally, by substituting all these values, the capacitance of a single isolated sphere coated with dielectric is given by the formula C is equal to 4 pi 1 by epsilon 1 minus 1 by A minus 1 by R1 plus 1 by epsilon naught R1 farads. So assessment questions: what is a spherical capacitor? Capacitance of a spherical capacitor, isolated sphere. Thank you.